Welcome to today's video on Cambridge IGCSE Mathematics 0607 and 0580. The topic for today is functions, where we will be looking at the subtopic graphs of different functions. The first type of function that we're going to be looking at is a linear function. Now, linear functions, if you graph them, they give us perfectly straight lines, and they can be in the format of y is equals to ax plus b. Now, you need to remember that y is equals to ax plus b. This can also be seen as y is equals to mx plus c. So y is equals to ax plus b and y is equals to mx plus c. This is denoting the same type of function, where m or a is the gradient of our line, which is the slope of the line, and b or c would be the y-intercept, or where the graph is crossing and intersecting the y-axis. The second type of function that we are going to be looking at is quadratic functions. When we see quadratic functions, they're always going to be in the format of ax squared plus bx plus c. Now, depending on the value of a, our function can look like a maximum function or a minimum function. If the value of a is positive, then we say the graph would be a U-shaped graph, which is a minimum graph. And on the other hand, if the value of a that we have is negative, then we would instead get an edge-shaped graph or maximum graph, which would look something like this, where our graph is cutting the x-axis. So that's this point of the graph that I can see here. These are also known as the roots of my function. So the shape that we get here when we get quadratic functions, this shape is generally known as a parabola. The next type of function that we're going to be looking at is cubic functions. Now, cubic functions come in the format of ax cubed plus bx squared plus cx plus d, and the highest power that we would be able to see would be a cubic power, or to the power of 3. Now, when we have cubic graphs, we can say that it can be a positive cubic graph or it can be a negative cubic graph. And to classify a graph as a positive cubic or a negative cubic graph, what we have to do is we have to look at the value of a. If the value of a is positive, then we say that's going to give us a positive cubic graph. And if the value of a is negative, then we say that's going to give us a negative cubic graph. Now, when we have cubic graphs, unlike our quadratic graphs, we don't just have one maximum or minimum point. We would have both the maximum point and a minimum point. So we have two turning points. One would be a maximum and the other one would be a minimum. Now, if we have positive cubic graphs and we look at the graph from left to right, we would be able to encounter a maximum turning point first, and then we would be able to see a minimum turning point. So looking at our graph from left to right, I can first see a maximum turning point over there, which I've marked in red. And then I can see a minimum turning point over here that I've marked in blue. On the other hand, if I'm looking at a negative cubic curve, then what we would be able to see is that if you look at the graph from left to right, we would encounter a minimum turning point first, and then a maximum turning point. So let's have a look at this graph here. Over here, I can see that the first turning point I encounter when I look at the graph from left to right is a minimum turning point. And then afterwards, I would be able to encounter a maximum turning point, making this a negative cubic. So negative cubics have an a that's less than 0, and positive cubics have a value of a that would be greater than 0. The next graph that we're going to be looking at is our reciprocal graphs. Now, our reciprocal graphs is where we would have our x value in the denominator. So, for example, a over x, and because x is in the denominator, we would get graphs which we would call the reciprocal graphs. And your reciprocal graph would look like this, where you would have your graph always going towards the y-axis, but never touching it, and towards the x-axis, but never touching it. And in this case, we would say your y-axis and your x-axis act as the asymptotes of our graph. So we call them the asymptotes because the graph keeps moving towards them, but it would never reach them. Now you need to also remember that if you instead have a graph of negative a over x, you would have the same shape, but instead the graph would look something like this, where again, your y and x axes would act as asymptotes, but the quadrant where you find your graph would now be different. The next graph that we are moving on to is our exponential graphs. Now, when we deal with exponential graphs, we have a condition that our a value here, it needs to be positive and it cannot take the value of 1. So when we have graphs in the format of a to the power x, then this would generate exponential graphs. Now, exponential graphs would give us graphs that look something like this. Again, you would never have your y values reaching to 0. So we would say the x-axis would act as the asymptote of our graph because the graph is getting very close to the horizontal axis, but it will never touch it. Now, these types of exponential functions can either represent an exponential growth, something like compound interest, or it can even represent exponential decay functions. The next graph that we would be discussing is our absolute value graphs. Now, when we talk about absolute value graphs, these are graphs where the values of it would never reach a negative. So our y values would only be positive values, but never negative. And an easy way to identify these types of graphs is noticing that these graphs would have very, very sharp turns. So looking at this graph, I can see it has a very sharp turn at this point here. So this is an absolute value function, and I can see that my y values are never reaching negative values. The smallest y value that this would reach would be the y of 0, and negative values for absolute functions are not possible. It's very important that we also recognize trigonometric functions. So we have 3 separate trigonometric identities that we would be focusing on for the syllabus. That's sine, cosine, and tangent. Now, looking at our sine graphs usually come in the format of a sine x. And this graph for our sine, it does not start at our origin, but it does pass through the origin. So we can see that we do have the sine graph that begins before the origin. So it does not start at our origin of 0, 0, but it does pass through or intersect our origin. Now, something about the sine graph that you need to know is that it repeats itself every 360 degrees. And we say the period of the sine graph is 360 degrees because that's where it repeats itself. And if the value of a here is 1, then the maximum value your sine graph can take would be 1. And the minimum value that it can take would be negative 1. The next trigonometric function that we're going to be looking at is our cosine curve. Now, your cosine curve is very much similar to your sine curve. We can see that it does not pass through the origin. It does not pass through 0, 0. But just like the sine graph, it also has the same period. It has a period of 360 degrees where it would repeat itself every 360 degrees. And if the value of a here is going to be 1, then the maximum value that your graph would take would be 1. And the minimum value that your graph would take would be negative 1. Let's have a closer look at our sine and cosine graphs. We can see that our sine and cosine graphs are always between the range of -1 to 1, and that the sine graph passes through the origin, whereas our cosine graph passes through 1 on our y-axis. Now, both the sine and cosine graph are periodic, and they repeat itself every 360 degrees. But if you look at the sine graph, I can see that for different values of sine. So I'm just going to take, for example, the sine of 90 and the sine of -90. So the sine of 90 is 1 and the sine of negative 90 is negative 1. So if I take an angle for sine and also look at its negative angle, then the values that I get for the sine would also be negative. On the other hand, if I do the same thing for my cosine graph, if I look at the cosine graph and if I look at cosine 180, so cos 180 as well as cos minus 180, we can see that the values for the cosine of an angle and the cosine of that negative angle, they're not going to be different. They're actually going to be exactly the same. The final trigonometric identity that we're going to be looking at is our tan graph. Now, our tan graph is very much different to both our sine graphs and cosine graphs. And we can see that it does indeed pass through our origin, but it takes a very different shape. And the reason for this different shape is because our tan graph has asymptotes. Other characteristics of our tan graph is the fact that it's periodic every 180 degrees. It's not a continuous curve, unlike the previous two trigonometric graphs that we looked at. And its asymptotes are vertical asymptotes that we can see at 90 plus or minus 180 degrees. So I would see a vertical asymptote at 90, 270, but also negative 90, negative 270, and so on and so forth. When we have the tan graph at these asymptotes, so like I mentioned, 90, 270, negative 90, or negative 270, then the values for tan would be undefined at these points, which means that if I enter into a calculator tan of 90, we're going to get an error message because tan is not going to be defined, because we say the range of tan at those points can be from between negative infinity to positive infinity. And by looking at this graph here, we can see that the graph is repeating itself every 180 degrees. So this pattern over here, it repeats itself every 180 degrees. Moving on, we're also going to take a closer look at what asymptotes are. Asymptotes are a straight line that constantly approaches a given curve but does not meet this curve at any until an infinite distance has been passed. So basically, asymptote is a line a curve is approaching as it moves towards infinity. Now, when we give asymptotes, I can see that in the graph that I have been given here, this is a reciprocal graph. I have the asymptotes as being my y-axis and my x-axis because my graph is approaching the y-axis and it's also approaching the x-axis, but it's never meeting them. Now, generally, if you wanted to draw your asymptote, you would use dotted lines to show this. And I can say my asymptote here, this is the value, this is the line y is equals to 0, and this is the line x is equals to 0. So there we go. That's what we have for asymptotes, and that's all we have in today's video. Thank you.